In this lesson, we'll put into practice the concept of intersecting graphs to model real-world situations. To model a word problem using a system of linear equations, which is just a fancy way of saying two lines, you must first declare your variables using a let statement. Then, create each of your equations. There are two types of linear system problems that we can model. The first is when you have a single scenario under different conditions. Here's an example of a single scenario with two separate conditions. We're told that Jason weighs 6 kilograms less than twice Bill's weight. We're also told that the sum of Jason and Bill's weight is 102 kilograms. We're asked to calculate each of their weights. We'll begin with a let statement that states that J will represent Jason's weight and B will represent Bill's weight. Jason's weight, again, is twice Bill's weight, less 6 pounds. We can represent this scenario with the equation J equals 2B minus 6. We know that the sum of Jason and Bill's weight is 102 kilograms. We can model this with the equation J plus B equals 102. Now that we have two equations, we can graph them and look for a point of intersection. When we graph these two equations, we can see that they intersect at the point 36, 66. The 36 represents Bill's weight, and the 66 represents Jason's weight. In this example, we have two scenarios under similar conditions. Carl's towing charges $80 plus 22 cents per kilometer. Bev's towing charges $70 plus 30 cents per kilometer. We'll let C be the total cost of towing and K represent the number of kilometers towed. Carl's towing can be represented by the equation C equals 0.22K plus 80. Bev's towing can be modeled by the equation C equals 30K plus 70. We'll model these two equations on a Cartesian plane with kilometers representing the x-axis and cost represented by the y-axis. When these equations are graphed, we can see that the point of intersection is 125, 107.5. Now you're asked, which towing company would we use? Now this would depend on how far a car needed to be towed. If a car had to be towed less than 125 kilometers, it would cost less to use Bev's towing. At the 125 kilometer mark, both towing companies would charge the same total cost. Anything further than 125 kilometers would make Carl's towing the cheaper option. This question is another example of two scenarios under similar conditions. Jill makes two types of quilts. The first type costs $25 for fabric and $40 per hour for hand quilting. The second type costs $50 for fabric and $22 per hour for machine quilting. Now we're asked, for what number of hours would the quilting job cost the same? The first type can be modeled with the equation C equals 40H plus 25. The second type can be modeled by the equation C equals 22H plus 50, where C is the total cost and H is the number of hours. When these two equations are graphed, they intersect at approximately 1.4, 80.6. This point represents a scenario where the cost of quilting both types is the same. The point represents 1.4 hours of work and a cost of $80.60. Anything that takes less time would be cheaper if quilted by hand. Any quilting job that took longer than 1.4 hours would be more economical to print using the machine. This question represents a single scenario under different conditions. A band held a concert in its hometown. A total of 15,000 people attended. The tickets cost $8 per student and $12.50 per adult. The concert took in a total of $162,500. How many adults came to the concert? Model this problem. Let X be the total number of adult tickets sold, and let Y be the number of student tickets sold. We know that the total number of adults and students equaled 15,000 people. We also know that 12.5 times X represents the total number or the total amount of adult ticket sales, and that 8 times Y represents the total amount of student ticket sales. We also know that the total amount of ticket sales was $162,500. So we can say 12.5x plus 8y equals $162,500. When we graph these two equations, we get a point of intersection of approximately 9,440 adults and 5,500 students. This is about as reasonably accurate as we can hope to be just by looking at the graph. When we do this, we find that we're not accounting for 60 people. This is pretty close, given that we're trying to predict small squares on a Cartesian plane, but this demonstrates the shortcomings of using this method for determining the solution of two intersecting equations. In future lessons, we'll see other methods that are much more accurate than simply visually looking at a graph.